Hello physics students. Today we're going to take everything that you understand about motion in a magnetic field and we're going to put it together so that you can understand a device called the mass spectrometer. Now, a mass spectrometer can measure the masses of single atoms, ionized, or it could be used to separate isotopes out. As you might remember from chemistry, take chlorine, for example. It is made of atoms that have an atomic number, some of them 35 and others 37 in a stable form. The mixture together of some 35s, some 37s, gives you an average atomic mass of 35.45, I think it is, something like that. But how do you determine these masses? How do you determine the percentages of these isotopes? Well, you have to find some way to manipulate the single atoms. That happens in the mass spectrometer. Now, the mass spectrometer, there are all kinds of ways they're created. You can look them up online if you want and do just like a Google search and then search the images. But in the AP curriculum, it typically takes a form like this. Mass spectrometer is generally made of 3 regions. Sometimes only 2, I'll mention that in a minute, what 2. But basically what you have is you get some kind of ion and you accelerate, like I mentioned, chlorine. So chlorine becomes -1 charge when it gets an extra electron to get into a stable form. So you get this ion, you put it in one region and you accelerate it up to speed. Why? Because there's a voltage over here producing an electric field. And from the way that this battery is drawn, even if I didn't put this minus sign here, you could see that the ions have to be negative from the way voltage 1 is drawn. The electric field will point from plus to minus like this. And so positives will accelerate this way, negatives will accelerate that way. So this charge gets accelerated up to speed. And then we have a plate here. So this is like a capacitor, but there's a hole drilled here, or a slit or something like that. So many of these ions strike this plate, but some of them pass right through this hole. Now, once that's up to speed, we would like to, for our experiment, select out the right velocity or have control over what velocity the particles will have eventually when we start using the spectrometer part of this. So we have another region where we have crossed electric and magnetic fields. So there's another voltage here between these 2 plates, and as you can see, there is an electric field that points from plus to minus like this, and then that creates an electric force in the for the negative ion, opposite direction electric field, in other words, upward. And then there's a magnetic force, because there's a magnetic field and a moving charge. And if we use our right-hand rule, we can determine that that force is to be in the downward direction. How? Well, I put my index finger in the, and by the way, not this right-hand rule, right? This one. This is for magnetic field around a wire. This is for force when something's projected with velocity through the magnetic field. So here's the velocity. My 3 fingers are already into the board for the magnetic field here, and my thumb points up. And so because this is a minus, it actually feels a force in the downward direction. So you got these 2 forces, and as I mentioned in a previous video, motion in a magnetic field, this force depends on velocity, this one does not. So if a particle is moving slow, comparatively speaking, this will be too small and the electrical force will dominate a curve this way. If it's moving fast compared to the ideal or the critical value here, then this force will be larger and this will curve down. But if it's moving just the right speed for these 2 to balance, this will pass undeflected and be able to go through that second hole in this plate over here. In this region, the electric field no longer exists, but we still have the magnetic field and still the magnetic force, which by the right-hand rule again points down like this. And that becomes, a centripetal force. And this curves in circular motion, and it's this ion will strike here. You could put different detectors here and see which detector strikes. Then you'll know the diameter and therefore the radius, and you could maybe solve for the mass of the particle. So that's how it works. 3 regions: an accelerating region, a velocity selector region where we have these 2 equal forces, and then the 3rd region where we only have 1 electromagnetic force, the magnetic, which causes circular motion of different radii depending on the mass. And that's how we separate out those masses. Of course, that's how it works. You need to be able to do an analysis with our understanding of the equations of electricity and magnetism. So, oh, by the way, let me create a pause before I go on to the analysis for you to do your best to copy this down. Try and draw the details accurately as you can. So, go ahead and do that now. Okay, so let's take a look at region 1 where we're accelerating the particle from rest. So, the easiest way, we could figure out the speed through Newton's laws, acceleration, so in kinematics, but it's easier just to use energy conservation. The electrical energy in the beginning, when this particle's over here and not moving yet, will disappear as the ion goes through that voltage and become kinetic energy. So this is before, that's after. We fill in the pieces of what kinetic energy is, what electrical energy is, and boom, we get the speed by solving for this, by solving for V. And again, this is voltage 1, the accelerating voltage, not the voltage here that produces this electric field, which acts in the other region. Now, the thing I want to point out as I label this equation 1, technically this is only an approximate value because these ions all the way on the left over there, they're not beginning at rest. Otherwise, the sample would be at absolute 0. And that's not what happens. You start with things already moving because of the thermal energy. So this technically has another kinetic energy over here. And furthermore, some of these ions might start over here, so they have less energy or less speed, or they might have kinetic energy, have more speed. So this is, again, only an approximate value. So that's why we need region 2. I'll go on to that in a moment. But first, let me create a pause to allow you to copy this down. Okay, so as I said, this is a range of velocities that are close to this. We make the 2nd region, the velocity selector region. Here's a little note. It's not always included in an AP problem. Sometimes we just have region 1 and region 3, and we assume that this is truly the speed coming into the magnetic field. So just be aware that sometimes it's simplified by this region not here. So I put the notes here of what I explained before. Particle A too slow, this one too fast, and this one, quote, just right. What do we mean by just right? We have the 2 forces balance, and so that's constant velocity motion, 0 acceleration. And then we fill in the pieces of what these forces are. The magnetic force is QVB sine theta. Of course, the velocity here and the magnetic field are 90 degrees to each other, so that's why I put in 90 degrees there. And the electrical force is simple, just QE, that's the magnitude. Notice the charge of the ion drops out, so whether it's doubly charged, singly charged, triply charged, doesn't matter, the charge drops out. And then the speed is the electric field over the magnetic field. And technically we could stop there, but we could also substitute out what the electric field is, because if this is a parallel plate capacitor, then the voltage is equal to ED. And so you can solve for E, which is voltage over distance between these 2 plates, and you get this expression. And it's kind of a very interesting expression. Oh, let me just create a pause to allow you to copy this down, and I'll explain. Okay, what's interesting, or at least what I find interesting in this in that equation is, we think of atoms, single ions, as kind of this intangible thing. You can't grab one ion. Can't grab a chlorine atom, it's too small. You could grab zillions of them all together and then you got a little sample of chlorine, right? But one atom, we have control over these single atoms. We can select whatever velocity we want with a simple power supply that we used already several times this year in our experiments, and a voltage dial. We crank up the voltage and you pick single ions here, whole bunch of, you pick the ones that are moving faster by just turning that voltage dial on the power supply. Do you want ions that are moving slower? Do you want to select slower velocities? Just take that dial and turn it down to a lower voltage. And then now you have ions, you're like almost like grabbing the ions that are moving slower. So again, so fascinating that with voltage dials, you have control over single atoms. Okay, fascinating. But nonetheless, there's the expression for the speed of these particles. Finally, we get into region 3, where we can now measure the mass of these things. We've got them going up to speed. We've picked what velocity we want. Let's see if we could solve for the mass. So, let me make some room. For our analysis of region 3. Well, it's technically all a mess, but this is where we put it into the magnetic field. And in this region, the centripetal force comes from the magnetic force. And as I mentioned in the previous video, this does not mean there are two forces that are equal and balanced. Then the thing would be going in a straight line. Like over here, when we said these two are two forces that are equal, zero acceleration, straight line. This is saying we only have one force, and it creates circular motion. So this force is the centripetal force. Just a little side thing that I like to keep emphasizing. Otherwise, sometimes people lose sight of what these equations actually mean. So this is mv squared over r for any circular motion. I don't care if it's a rock on a string or a chlorine ion in a magnetic field. This is what the magnetic force must be, or the centripetal force must be. And what we have in this instance is QVB sine 90 degrees, again in that third region that I erased. And so I'm just going to put like a little line here because this is the big idea, but there's two possibilities here, maybe more, I don't know. But let's suppose I solve for m. So I see one of these velocities goes away, so all I have is QB over here, and then I multiply by r. QB r, and divide by the one velocity over here, so here, okay? And now I've solved for the mass of the single ion in kilograms. Also remember that you can get rid of this velocity by either plugging in equation 1 or equation 2 and get rid of that velocity. So again, just based on voltages, or here voltages and distances, you can solve ultimately for the mass of the particle, okay? And so that again is how I can measure mass with this. Another possibility is maybe you solve for the radius here. So if you solve for the radius, what you have is mv on the top and qb on the bottom. Okay, and then just a reminder that this is also in the picture that I had drawn over here, where we had the diameter like this. So you have to also sometimes remember that this is 1/2 the diameter of where we put the detector compared to the hole that the ions came through. So this, if you solve for this, maybe you want chlorine with an atomic number 35. So you would solve for where to put the detector to catch those ions. Or maybe you wanted the ones for the mass of 37. So then you would solve for the radius and find out that if you want to catch the ions with an atomic number of 37, you would have to put a detector here, and then those would crash in and you could be collecting those. So that is the mass spectrometer, okay? So again, I just want to emphasize 3 regions in the kind of problems you'll encounter on the AP. Region 1, energy conservation. Potential electrical QV equals kinetic energy, 1/2 mv squared. And you solve for the speed. The second region, velocity selector, the electrical force QE equals the magnetic force QVB sine 90. And you solve for the speed that you're selecting in that second region out of these approximates. And then the third region, the centripetal force is the magnetic force. In other words, mv squared over r equals QVB sine theta. Those are the big analysis, the three big things you need to remember about a mass spectrometer. So, I hope you enjoyed the video. I hope you enjoyed the physics and the analysis. I'll see you in the next physics video.